We've seen that currents can cause magnetic fields. Well, magnetic fields can also induce currents. Michael Faraday discovered that when a magnet is pushed into or pulled out of a coil of wire, a current is created in the loops. Here we see an animation of what's happening as a magnet is pulled and pushed into a magnetic field repeatedly. The key observations are that 1. The current is created by a moving magnet. It's only when it's moving that there is a current, you can see in the needle being deflected. When it's sitting stationary in the coil, there's no current. Once pulled out and sitting stationary, there's no current. But when it's moving, there is a current. The current depends upon how the magnetic field and the coils overlap. The stronger the magnetic field there is for the coil, the stronger the deflection of the needle, or the greater the current. The direction of the current depends upon the direction of the moving magnet. When the North Pole is being inserted into the magnetic field or pushed in, the needle deflects to the right. When it's pulled out, the needle deflects to the left. So what's going on? We thought that voltages or batteries cause currents. Does the moving magnet create a voltage? And the answer is yes. A changing magnetic field on a loop of wire acts like a voltage. You can imagine, here you have a loop, and we have a magnet that's going in and out. That'll induce an oscillating voltage. If we look at another way of doing this, we could have, again, a loop, and we put an oscillating current through a second loop. The oscillating current in the second loop creates a changing magnetic field. That changing magnetic field will create an oscillating voltage in the other loop. So there's a tight tie between currents and magnetic fields. To understand this, a unit called magnetic flux is created or defined, and it's a measure of the overlap of the magnetic field and a loop of wire. The flux phi sub b, or the magnetic flux, is equal to the integral of the magnetic field dotted into dA. dA is a small little piece of the area of the loop. It is perpendicular to the loop, and its magnitude is that area of that small piece. The dot product between B and dA gives you that overlap. Faraday's law uses this. It says that the V induced is equal to the time rate of change of this flux. So the flux has to be changing with time for voltage, and it also depends on how much B and how much A overlap. This is for a single loop. If the magnetic field is the same over the entire loop, then V induced is equal to minus d phi dB, the time derivative of d phi, and it's equal to minus dB dot A, because B and the A is the same over the whole, B is the same over the whole area. For a tightly packed coil, so there's lots of loops, but they're all about in the same spot, and so the flux is the same through all the loops. The induced voltage is just N times this d phi dt, or minus N times the time derivative of B dot A if the B field is constant over the entire loop. Let's take an example. If there's a pulsed electromagnet and that produces a magnetic field that goes linearly from 0 to 1 Tesla in 1 second, we place a 100-loop coil within that magnet, and it has an area of 1 times 10 to the minus 4 meters squared. This is about 1 centimeter by 1 centimeter. Then we find that the magnetic field is perpendicular to the area of the coil, so it's put in that. So B and A are parallel, and only B changes with time, so that V induced is this minus N d phi dt, so it's the number of loops times the magnitude of the area times the time rate of change of the magnitude of the B field. And that's equal to the number of loops, which is 100, times the area, which is 1 times 10 to the minus 4 square meters. And the slope of this linear change from 0 to 1 Tesla is 1 Tesla per second, so it's just 1. So that the voltage created the induced voltage is just minus 0.01 volts. Let's look in more detail at Faraday's law. We've seen that a change in the magnetic field induces a current in a loop. But that induced current also creates a magnetic field. This induced magnetic field is in the opposite direction to the change in magnetic field that created the induced current. So there is some sort of circular causality going on here. Let's look at a case where the B field is increasing with time. We have a loop. We have initially a B1. At a later time, it becomes B2. Then the change in B is just the difference between B2 minus B1. In this case, since B2 is bigger than B1, the difference is in the same direction, so that the induced B field is to the right, opposite the difference between B2 and B1. That creates a current that goes around the loop as shown. So this is the current that you need to create that induced B field if you use the right-hand rule. If we look at a case where B is decreasing with time, now we have a fairly large B1 initially, and then we go to a smaller B2 at some later time. Now the difference between the two points in the opposite direction, so that the B induced is now pointing to the left. This creates a current that goes around the loop in the opposite direction. Again, to create a B field in that direction using the right-hand rule, you have to curl your fingers in the opposite direction. We could also look at this in the case of a magnet moving into and into a loop. Here we have our loop and a magnet. When the magnet is moving, the induced current in the loop creates an induced magnet, or you can imagine an induced magnet that tries to push the real magnet back. So if we look at that started, the imaginary magnet appears, and then it disappears when the motion stops. But let's go back for a second and look at what type of magnet it is. We see that the imaginary magnet has poles that are in the opposite direction, so that we have a north facing a north, and that is and that will repel or try to repel the magnet that's being pushed in. So you're working to push. You have to work hard to push the magnet into the loop.